This simulation models a high-energy architectural X-ray beam passing through a homogeneous block of soft silicone. The result is a completely flat, featureless shadow. In human anatomy, the attenuation coefficients of glandular breast tissue, connective tissue, and adipose fat are nearly identical. A standard high-energy diagnostic beam passes through all of them equally, leaving no contrasting shadows to analyze. To differentiate these structures, the system must operate within a highly specific, narrow energy band. This forces variations in photoelectric absorption between similar soft tissues, establishing visible contrast. Simultaneously, the system has to maintain an ultra-high spatial resolution capable of detecting microscopic calcifications, and it must do so without exposing the patient to radiation levels above strict safety limits. Mammography is not a modification of standard radiography. It is a bespoke physical architecture engineered from the subatomic physics upward to solve these specific failures. This chart plots X-ray photon energy against beam intensity. The highlighted vertical band marks the 17 to 20 kiloelectron-volt range, the mathematical ideal energy window to maximize photoelectric absorption in standard breast tissue. Engineers equip the tube with a molybdenum target. When electrons strike molybdenum, they produce characteristic X-rays defined by the metal's exact atomic structure. Two massive, sharp characteristic spikes erupt at exactly 17.5 and 19.6 keV, aligning with our targeted absorption window. However, the target also emits a high-energy Brennström tail, a broad spectrum of background radiation. These higher-energy photons degrade image contrast. To strict this background radiation, the beam passes through a molybdenum K edge filter, a physical point where attenuation abruptly spikes above a specific threshold. At 20 keV, a steep drop-off curve drops onto the graph, physically cutting off the higher energy tail. This target and filter pairing lacks penetration power for highly dense tissue, which would force the machine to apply unacceptably high radiation doses. By utilizing a rhodium filter, or utilizing rhodium for both the target and the filter, the K-edge shifts to 23.3 keV. This maintains penetration. For extreme cases like large implants, a tungsten target is paired with a rhodium filter. Because tungsten does not produce characteristic X-rays in this range, the total beam intensity drops, requiring longer exposure times to achieve the necessary dose. Target and filter selection is an active physical compromise, balancing soft tissue contrast against rising radiation doses. Moving to the macro scale, the breast anatomy presents a geometric problem. The tissue structure is thickest at the chest wall and tapers down to its thinnest point at the nipple. We compensate using the anode heel effect. An angled target anode absorbs X-rays traveling through its heel, creating higher beam intensity on the cathode side. To exploit this, the machine aligns the high-intensity cathode side over the thickest tissue at the chest wall. The heavily attenuated anode side rests over the thinner nipple region, equalizing exposure across the density. To maintain this alignment, the X-ray tube and detector are mounted to a C-arm, with the focus detector distance securely fixed at 65 to 66 centimeters. A longer distance ensures the X-ray photons travel in more parallel lines, which reduces geometric unsharpness on the detector and lowers the patient dose. Conversely, a shorter distance allows for a higher beam intensity at the receptor, permitting shorter exposure times that prevent movement unsharpness. The 65-centimeter length is a strictly calculated midpoint, balancing geometric sharpness against kinetic blurring. Resolving microscopic calcifications requires exceptionally small focal spots at the X-ray source. This diagram outlines the optics. A broad light source creates thick, blurred edges, or penumbra, on the detector. A pinpoint source casts a sharp silhouette. Mammography utilizes a fine focus pulled down to 0.1 millimeters. These tiny focal spots restrict the tube's power output, requiring low exposure times. The only physical intervention allowing this is tissue compression. Standard compression is set between 100 and 150 newtons, with a safety maximum of 200 newtons. Reducing the physical thickness drastically lowers the required radiation dose to penetrate the tissue. A thinner cross-section also reduces the probability of Compton scatter occurring within the tissue. Anatomically, compression mechanically spreads tissues out, unmasking hidden structures that would otherwise overlay one another. Geometrically, forcing the tissue layers closer to the image receptor directly reduces geometric unsharpness. And kinetically, immobilization prevents movement unsharpness during the necessarily longer exposure times. This mechanical force is a physical prerequisite. It makes the low-energy beam viable at safe doses. Despite compression, scatter still occurs. Moving anti-scatter grids are mandatory for filtering out rogue photons across all standard contact images. The primary exception to grid usage is during magnification views, which utilize the fine focal spot. This split-screen ray tracing shows the two methods. On the left, scattered photons are physically blocked by lead strips. On the right, during magnification, an elevated platform creates a large air gap. Scattered photons diverge and miss the receptor. Historically, automatic exposure control, or AEC, evaluated density to stop an exposure and prevent overexposed film. Modern digital AEC uses a rapid pre-exposure to run precise density checks, evaluating the rate of beam hardening and dynamically altering the dose rate. Because digital windowing can rescue poorly exposed image data, the digital AEC's function focuses on patient dose management and optimizing the detector's signal-to-noise ratio. The digital receptor and the AEC act as final systemic gatekeepers, ensuring the carefully tuned beam stays within its mathematical parameters. Despite spectral tuning, geometric alignment, and heavy compression, a 2D projection still suffers from superimposed tissue that can hide pathology. Breast tomosynthesis is the architectural evolution of the C-arm, designed to overcome this limitation. In this schematic, the X-ray tube traverses an arc above the breast, acquiring discrete images from varying angles by firing individual pulses. Two variations exist. On the left, the bottom detector remains stationary. On the right, it actively rotates in sync with the arcing tube. The system runs all this data through reconstruction algorithms to output clean planar images of different depth sections. This yields immense clinical benefits, delivering exact precision in lesion localization and a reduction in false positive recalls. However, these benefits carry high logistical costs. Tomosynthesis requires approximately double the standard radiation dose. It struggles with artifacts caused by high-contrast surgical clips, and it demands exponentially more digital data storage. Radiological engineering is a science of compromise. We trade radiation dose, mechanical force, and processing overhead for the ultimate prize: perfect spatial and contrast resolution.